All right, assignment 3.8, we're going to look at gravity word problems. Hey, I really encourage you, I can't show you on the paper, but watch this video. We're going to do questions 1 and 2 together, but watch this video. Here we have a punter. Oh boy, I'm going to draw little stick figures. This is going to be interesting. We've got a punter who can take a football, and of course, boom, he can kick that thing up in the air, and of course, it's going to come down and land eventually. But the best punters in the NFL, the amount of time this football is in the air, it's called hang time. That's what they call it in football. The best punters in the NFL, they can get a hang time of over 5 seconds. Now, if you're not impressed by that, go out and try it yourself. Try kicking something. I don't care if it's a soccer ball, football, kickball, whatever. Try kicking something in the air and then timing 1001, 1002, 1003. See if you can kick something in the air for 5 seconds. It's impressive. Okay, but at any rate, I'm going to introduce you to a formula today. There's a formula. See, quadratic functions can be used to model anything that deals with acceleration or deceleration. Okay, well, when a football is kicked through the air, the acceleration of gravity is acting on it the entire time. And so it's kicked with this really high upward velocity. But what happens is, so it comes off the foot really fast, but then gravity slows it down, slows it down, slows it down. And for this split second, the football is actually just hanging in the air where it's not going up and it's not going down. It's just hanging there. But then gravity starts pulling the football back down to earth, and it accelerates. As that football falls, it's going to go faster and faster and faster. Okay, so we can model this with quadratic functions. This is one of the most important applications of quadratics. Okay, a lot of things about flight related and things traveling through the sky and orbits, man, it all centers around quadratic functions. So at any rate, let's take a look at the data that's given to us in this problem. Okay, the first punt in the above video leaves the punter's foot with an initial upward velocity of 88 feet per second. And I had a little error on this earlier in the video. I had to flip it. We're going to call this V, the initial velocity. And if you're curious, that's right around 60 miles per hour. Okay? And then, so that's how fast it comes off of his foot when the punt leaves his foot, 88 feet per second. And then it had an initial height of 2.5 feet. So a punter doesn't kick a football right off the ground. It's going to be hanging in the air. Here, this football was already 2.5 feet off the ground when he kicks it. We're going to call this H. And then we have this hang time formula that works if you're in feet. Y equals, let's plug in the numbers that we know. Y equals negative 16 x squared. And then we're going to take our velocity, 88 feet per second. We're going to put it in for V. And then we're going to take our initial height, the 2.5. We're going to put it in for H. And this is the function that will model the flight of this football. Okay? And at the end of the video, I'm going to show you how to check your answers on Desmos. You'll be able to see, like, you plug this into Desmos, you're going to get like a perfect representation of this football flying through the air and how high it goes versus how long it's in the air. Okay. Now, if you're curious where the negative 16 comes from, as long as you're on planet Earth and using feet and seconds, this number will always be negative 16. This is actually half of the gravity. The gravity on planet Earth is negative 32 feet per second. And it's negative because gravity pulls things back down to the ground. And so you always take half of that in the formula. All you need to know is that we're always going to keep the negative 16 here because as long as we're on planet Earth. Okay? But then the 88 and the 2.5, that will change depending upon the problem. Okay, so let's look at question 1. According to this formula, this function that you just made, how high did the first punt go in feet, round to the nearest tenth of a foot? Well, if you want to find out how high an object flying through the air goes, we're going to have to find the vertex. See, the vertex here is the highest that this ball is ever going to go before it starts turning around and coming back down towards the earth. So to answer question 1, we simply have to find the vertex. Now, we learned the vertex formula in our last lesson. X equals negative b over 2a. And so here's our values. We have that a is negative 16, b is 88, c is 2.5. So let's plug in. For x, we're going to do negative, or the opposite of 88, over 2 times negative 16. Now, please, 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 at this point, promise me that you will always, on the Vertex formula, that you will always multiply this 2 times negative 16 before you attempt to divide. So I need to do negative 88 divided by negative 32. Okay, this multiplication has to come first before you try to divide. So here, the x-coordinate comes out to 2.75. And then if you recall from the last video, now to find the y-coordinate, we're going to plug this 2.75 in for x. So let me write this out here. And then I won't even try to bore you by, I'm not going to make you watch me type this in the calculator. There we go. Type that in a calculator. We get 123.5 feet. Oh yeah, y value is 123.5. And so listen, this is our vertex. The vertex is 2.75 comma 123.5. Well, guess what? The x-coordinates here tell me the time. It takes 2.75 seconds for that ball to reach its maximum height. But then that y-coordinate is what gives me the actual height itself, 123.5. And it says round to the nearest tenth of a foot, so that's perfect, 123.5. Okay. Now let's look at question 2. According to the formula, how many seconds was the football in the air round to the nearest thousandths of a second? In other words, how long, here we're asking, how long until this football lands? Well, here we're going to be looking for the 0, also known as the x-intercept. And if you recall from the previous lesson, we have to use quadratic formula for this. Okay, so I'm gonna do a shortcut here. I'll kind of write out the formula and tell you the answers and give you an explanation. Give me a second. And let me walk you through what happened here. So here, I went to take my square root. I plugged everything into the quadratic formula. Went to take my square root, and it came out irrational. The square root of 7904 is approximately 88.9044. Now listen, my final answer has to be accurate to the nearest thousandth of a second. That's 3 decimal places. So at this point in the problem, if I want my final answer to be accurate, you really ought to go out to like 4 or 5 decimal places at this point of the problem. Okay? And then something else kind of unique happened. So I plug my 88.9044 into my quadratic formula. You'll notice when I did my addition here, I got this bizarre answer. I got an answer of negative 0.028. Okay, it's trying to say the ball was only in the air for negative 0.028 seconds. Now you'll notice in the context of this word problem, that answer makes no sense whatsoever. I'm actually going to cross it off. This would be, think of my graph. This would be if the football were to just like fall down out of the punter's hands and come straight down to the ground right here. We'd say that was like negative 0.028 seconds. But we're not interested in that. We're interested in this positive 0 over here. Now that one comes out really fantastically to 5.528. Okay, so this point up here looking at my graph would be at 5.528 comma 0. That's where the football touches the x-axis. Well, that's the same thing as when the football hits the ground. The football hits the ground 5.528 seconds after it was punted. And that is a really impressive hang time, 5.528. Okay, so stick around. I'll show you a little bit how you can plug this into Desmos. So here's how we're going to check our answers to questions 1 and 2 using Desmos. Now, when you first type in your formula, negative 16x squared plus, it was going 88 feet per second, so plus 88x. It had an initial height of 2.5. When you first type your formula into Desmos, it's going to look, I think, a little awkward. And you could try to like zoom out and see like how high this parabola goes, but even that I think starts to look a little awkward. So let me show you how to set the window. If you want this graph to really look good on Desmos so you can check your answers, I'd recommend going to this wrench up here and then adjusting your x-axis, all right? So the x-axis here is the number of seconds that the football is in the air. Well, we know that it's going to start at 0 seconds, and then we know like the best NFL punters can punt at 5 seconds in the air. So maybe I'll go a little bit beyond that, like 6 or 7 or 8. You know what? I'll do it to like 8 seconds. Okay. that kind of puts the 5 towards the middle of my graph. Now the y-axis then is the height of the football in feet. I know that the answer we got for our vertex was 123.5. So I'm going to try going higher than that, like 150. But then look how much better this graph looks now. Here you can really visualize this football flying through the air. Now at the very beginning, move that point just a little bit. At the very beginning, it starts, okay, at 0 seconds when it's kicked, it's 2.5 feet off the ground. That's where the punter kicks it. But then watch, you can imagine this 1001, 1002, 1003, 1004, 1005, 1006. Here you can check the vertex. We were correct. We said it was 123.5 feet was the highest this football went. And then we can check the 0. We were also correct. We said the football would hit the ground at 5.528 seconds. But isn't that a wonderful visual? You can see how, man, gravity, parabolas, or sorry, quadratic functions model gravity perfectly. It's almost like the language that gravity was written in just perfectly is modeled by quadratics, a variable being squared. All right, so there we go. There is your quadratic functions at work. Best of luck on this assignment.